Okay, in this presentation, what we're going to do is simplify the following expression, the following complex number, or complex expression, and express it in polar form. So here's our expression here. It is one complex number divided by another complex number. So to start out, what we're going to do is multiply above and below by the complex conjugate of this number here, the denominator. So let's multiply above and below by the complex conjugate of that. Now, so that is the square root of 5 plus 1, or sorry, plus I, and above and below by that. Now, just to be clear about something, the complex conjugate of this number is essentially the same number, just change the sign between the real and the imaginary. That is how you compute the complex conjugate. So we have a minus there, and as a result of that, we have a plus here. It's only incidental that the numerator is the same number. So let's multiply these out. If we're multiplying a number by its complex conjugate, essentially what we're getting is the absolute value. So it's the square root of square root of 5 plus 1 squared. So that's just a theorem. So it's the square root of the square root of 5 squared plus 1 squared. That's what happens when you multiply a number by its complex conjugate. You get the modulus. Okay, so that does not apply to the top of the line. We're not don't have the complex conjugates here, so we have to multiply them out. So what I'm going to do here is multiply the term on the right hand side by the square root of 5, then do the same thing by the square root of 1, or sorry, by 1. So square root of 5 times the square root of 5 plus the square root of 5 times I, okay, plus I times the square root of 5 plus I squared. Okay, and as we all know, I squared is equal to minus 1. So let's just replace that and put minus 1 there instead. Okay, so square root of 5 times the square root of 5, well, let's just call that 5 there as well. Okay, so we have 5 plus the square root of 5 times I plus the I times the square root of 5. So essentially the same number. Let's just start it in a new line here. So what we have here is 5 plus 2 times the square root of 5 times I minus 1. Let's just look at the denominator here for a second. And we get 5 squared. So that's 5 plus 1. So we get the square root of 6 there on the denominator. Okay. Sorry, I've just gone a bit too far here. Sorry, that should be just a 1 there. Minus 1. So it's minus 1 there, not an I. Okay. So just simplify that out a little bit more. We get 4 plus 2 square root of 5 times I all over the square root of 6. Okay, so that is how we would simplify the number. Now what we've got to do is express it as a in polar coordinates. Okay, so how do we do that? Well, let's actually just sort of separate this number out a little bit further. So we have 4 over the square root of 6 plus I times 2 square root of 5 over the square root of 6. Not the most easy number to work with, but we'll get by. Let's first off find the modulus of that. So let's go to a new slide. So 4 square root of 6 plus I times 2 square root of 5 over square root of 6. The modulus of that is this term squared plus this term squared, the square root of both of them together. Let's get that. That's 4 over the square root of 6 squared plus 2 square root of 5 over square root of 6 squared. Okay. Now, 2 times the square root of 5, I'm just going to replace that briefly with the square root of 20. If you just work that out there, just to sort of make it a little bit easier to look at. And I'm going to replace the 4 with the square root of 16. Just one sec. Probably wasn't worth all that hassle there, but there we go. So when we multiply them out, we get 16 over 6 plus 20 over 6. When we square them out, so we get the square root of 16 over 6 plus 20 over 6. That's the square root of 36 over 6, which is 36 over 6 is 6. So essentially, the modulus is the square root of 6. Okay. Now, what's the argument? The argument is, well, the argument of z equals a plus ib is as follows. Now, just actually recall from the last case that they are both positive numbers, okay? And on the Argand diagram, they are in the first quadrant, so you don't have to do any special operations to find the argument. They are both in the first quadrant of the Argand diagram, which means that's a relatively straightforward operation. This is the first, second, third, and fourth. Okay. If they were in the third or fourth, or if they were in any other ones, you have to be a bit more careful, particularly if they were in the third quadrant. But no, they're in the first quadrant. Both A and B are positive numbers, so this is a very straightforward operation. What is the tan of theta is B over A. Okay. So the argument is theta, and that's just the inverse tan of B over A. And again, just caveating that, just a sort of a slight note that is, if it's for the third quadrant in particular, you have to sort of do a little adjustment on that answer. It won't give you the full answer. For the first quadrant, this is fine. So that is equal to 2 over the square root of 5 over the square root of 6 divided by 4 over the square root of 6. Well, the square roots of 6 cancel out. Grand. 2 and 4 cancels out to 2. So we have 5, square root of 5 over 2. Okay. Now, this is a bit of calculator work here. What you could do here is essentially just get a bit of this is just a bit of calculator work, but you should find that theta equals 0.841 radians. Okay. So now we are ready to write out our expression z in polar form. We recall that the modulus is the square root of 6, and we call that r, the modulus, and the theta is 0.841 radians. So z is equal to the square root of 6 by cos 0.841 plus I sine 0.841. Or if you like it in the exponential form, z equals square root of 6 by e to the I 0.841. Okay, that's the trigonometric form and the exponential form of the polar form of Z. Alright, that's enough of that.